All righty, let's come to order here. So I emailed you out a homework assignment. I actually did it twice because I'm not sure I attached all the files to the first one, but anyway, I think I got it right. This is the actual assignment. It's just one problem. It's due a week. I want you to do an Excel sheet and email it to me. I just want you to calculate, basically calculate the electric bill and yeah, I guess that's it. So I also sent you the rate structure to use, which is Nashville. Let's see, I think it's this one. I think that's what I sent. But anyway, it's pretty much what we've been going through. So all your definitions and stuff are up here. Availability, character of service, base charges, adjustment, facility rental. Let me see, I don't know, do I tell you, I don't know if I put a voltage in this thing. You'll need a voltage. Looks like I got it open. Oh, no, there it is. Okay. Guess I have to send this again. Assume they're taking low voltage. I don't know, you can do, I don't care. 480 is fine. The POWER. I could email that out to you. You'll need that for the facility charge. I think the rest of it's probably pretty good. So facility reactive. These are the power factor charges, and they are paying penalty. They'll need to pay some penalty the way I set it up. And then seasonal periods and all that stuff's pretty much, I think, the same that we went over. Minimum bill, you won't have to worry about that for that month. So anyway. Okay, so we will pick up where we left off last time. Trying to get through a little bit on power factor here, and then we'll jump into the steam stuff. I'm going to send you a power factor assignment as well. But you'll, I don't know, I'll probably send you that over the weekend, something like that. Okay, so this is where we left off before. And so at the previous slide, we saw where power factor is 1. Basically what we're saying is all of this voltage and current are in phase with each other, which means that they peak together, they go through 0 together, and so they positive peaks, negative peaks all occur in phase. That's characteristic of an all-resistive load, and as far as the power factor discussion is concerned, that's the best, that's the most efficient use of the electricity. But with inductance in the circuit, this is what you usually see unless it's corrected. So we see over here voltage peaks here, and later in time, current peaks, okay? And then you look where they cross 0. If I can get my pointer there. So you see the voltage crosses here, and the current crosses here. So you can think about this in terms of time or angles. That is the, in an angular sense, that is the power factor angle. That's the phase angle between these two waveforms. And so in this case, it's 45 degrees. And so cosine of 45 degrees is the power factor. And we saw that back on the right here. In terms of the power triangle, we get the real kW at the top, the apparent power, or the kVA, which is the hypotenuse, and then the reactive power is the sine side relative to that angle theta. 1.73 is the square root of 3. So, you know, you could put more digits on it. I don't know why I didn't put square root of 3, but I didn't. So there we go, there we go. So that's the physical manifestation of what you would see on an oscilloscope. And remember, our voltage and current is the RMS, root mean square, of these waveforms. Okay, so I've got a little trumped up example here to show you why utility companies object to low power factor. So case one, let's say that we have a 100 kW electric resistance heating coil, maybe as part of some process, okay? So it's going to pull 100 kW of power with a power factor of 1 because it's just a resistance load. Case two, which we'll compare that to, let's say we have a fairly large motor, but it's, say, a 250 horsepower motor, but it's only partially loaded, okay? And it's loaded to the point that it's pulling 100 kW of input power. And the power factor on that, we're going to say, is 70.4%. So if you put a power meter on it, or the utility meter is going to see 100 kW for both of these loads. But you're going to see a big difference in current to supply that load because of the low power factor. And that 100 kW is equivalent to about 127 horsepower load on that motor. So it's, I don't know, 127 divided by 250. So, you know, it's not very heavily loaded for as big as it is. But you see that. You see that a lot. Motors get spec'd. Anybody spec'ing a motor doesn't want to burn it up. You know, if you spec it too small, it becomes a crispy critter. And then you get to buy a new one. If you spec it too big, it runs just fine. You may have a low power factor, but most people out there don't even know what that is. So, you know, your boss doesn't get very upset about something he doesn't even understand, you know? So anyway. Okay, so here's the calculation. Case one, real power, 100 kW. And I don't know why I picked 230 volts for this. I mean, it's possible. It could be whatever. I guess if the voltage is lower, the current has to be bigger, and it makes a better example. I don't know. But anyway, we'll use 230 volts in both cases. And so, you know, the power factor is 1, and the square root of 3 is the square root of 3. And so, you know, basically I just solved this equation for the current, and it comes out 251.3 amps is what it takes to supply this 100 kW with a power factor of 1. Okay. And there's the power triangle. It becomes a line because you have the kW and kVA right on top of each other. And so the triangle collapses. Where is it? So if this reactive power goes to 0, then this side comes up, and these two are just the same length, and they lie on top of each other. So instead of a power triangle, you get a power line, which is what we're showing on that slide. Okay. So that's about it. The kVAR is 0. The kW equals the kVA, and we're pulling 251.3 amps at 230 volts, so that's 100 kW. If that operates for 1 hour, it's 100 kWh. If it operates for 10 hours, it's 1,000 kWh. It's just however long it operates is what you have to pay for. You'd have to pay for the 100 kW demand charge, and you'd have to pay for whatever the energy was every month. Okay, so a little more interesting here. So this is still 100 kW load. So the power meter sees the same thing. Well, almost. There's one little piece that we'll talk about in a minute, but generally it sees about the same thing. So we're going to say it's 100 kW load, 230 volts, but now the power factor is 0.7042. Square root of 3 is the square root of 3. So you solve that thing for amps, and we get 356.9 amps, which has to be supplied by the power company. You know, that's part of the electrical draw of the plant. Okay, so you see the power triangle. If you, let's see, so the apparent power is 142 kVA, amps 356.9. Reactive power, just, you know, what, 142 squared minus 100 squared, square root, Pythagoras' theorem, that shouldn't throw anybody. So you calculate reactive power is 100.8 kVAR. Of course, you know, we put different units on this stuff, but I mean, it all works together in the power triangle. That angle is 45.2 degrees is what it comes out. And so down at the bottom in red, for this 100 kW, we need 356.9 amps minus 251.3 from the previous slide where the power factor is 1. So that's 105.6 additional amps because we have low power factor. Well, say if all of your loads are doing this, you're sucking all of this current from the electrical company and they can't sell it to somebody else. So if your power factor was 1, if you corrected this power factor to 1, the power company would have another 105.6 amps to sell to somebody else. That's missed revenue for them. And you know what? They don't like you very much because of that. And you know what? If this gets bad enough, they're going to penalize you. They're going to make you pay them extra money for the privilege of not efficiently using their current that they sell to you. And they can easily do that. And that's what power factor penalties are all about. Now, there's different ways they get calculated based on the rate structure. And we'll talk about that. I'm going to pull up a couple of different rate structures here in a minute and show you how that works. Questions? Yes, sir. Okay, loud. You got to yell at me. I'm sorry.
What does the 3-phase mean next to the volt?
It's if you look at the connections, you know, in say you open up the panels and look at the wires, you've got phase A, phase B, phase 3. It's 3-phase power. Like here, if I cut this open, I've got basically 2. I got a ground wire, but that's not. I've got basically 2. This is single phase, so it has just 1 phase and say a ground wire on it. But if you anything very large in an industrial setting is going to be 3-phase. So it has 3 power wires: phase A, phase B, phase 3. You can name them Alpha, Beta, Charlie. You can name them after your kids. You can call them ABC, 1, 2, 3. It doesn't matter, but you just have to designate this is phase A, phase B, phase C. And if you put a power meter on those, they won't read exactly the same thing. You know, I've got, I can show you some pictures. Let me see. I can show you some pictures. Let's see. Let's get out of this for just a second. We'll come back. Previews of coming attractions here. Look in the pumping presentation. Not that. Yes. Well, here. It's the best one. Where's Well, we got a couple. We'll flip through some of these here. Why this thing is so slow? Okay, so you see it pretty well here. So you've got 3 wires, 1, 2, 3. Phase A, phase B, phase C. You can name them whatever you want. 1, 2, 3. And if you were going to take power measurements on this thing, if you can get to, you probably come down here where you got a little bit of open wire. You can clip a CT on there, a current, what a transformer or CT, current something or other, the electrical thing. You just they open up. You can get them that open up, and they call them donuts. You can put them on there for permanent installation. They actually pull the wire loose and just stick it through a donut. It's a coil, and it picks up the magnetic field, the EMF around the wire, and transduces it into a current. So that's how you measure the current on the wire. For portable meters, they have them that they open up like a clamp, and you just clamp them around it. And so you clamp on this one, this one, this one, and then you get voltage. So you have to measure voltage and current, and then you take your voltage leads very carefully. And if you were on the one on the left, then you touch the leads to the other two for some reason, and that measures the voltage. And then the power meter will give you the actual watts. It'll give you the power factor. It'll give you everything right there if you have a real power meter. If you're too cheap to buy a real power meter, you buy a voltage meter and you record the voltages, the phase to phase, and then you clip on this one, you clip on this one, clip on this one, you just get amps, and then you get voltage. You average all that together, and then you have to guess a power factor if your meter can't measure it. And that's always a challenge. We'll talk a lot more about that. But that's what you mean by 3-phase power. Yes, sir.
So
Answer.
Is that where the square root of 3 comes from?
Is that where what?
The square root of 3?
That's exactly where the square root of 3 comes from. If you have single phase power, you leave that square root of 3 out. But if you go out in the industry, even a 1 horsepower motor sometimes will be 3-phase. Anything over a 5, 10 horsepower motor, they're all 3-phase. And one reason is they run smoother because you've got those 3 phases. If you put it all in 1 phase, you've got basically 60 cycles like this. But when you they space that out in time, so you've got 1 phase here, 1 phase, what's 3, 120, I guess they're 120 degrees apart. I can't divide 36 by 3, so this one, and then they space it out, and then they space it out. So it's much smoother because if you're delivering your power just boom, 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 it's more bumps in the road. But when you instead of every 360 degrees you go through a cycle, you go through one every 120 degrees, everything runs much smoother. So industry really likes 3-phase power. So just about everything is. Okay, we might pull that back. Loud, yell it.
Where did you get how'd you get the 45.3 degrees again?
How'd I get what?
45.2 degrees.
Oh, well, the cosine of this angle is what? 100 divided by 142. And then you go in your calculator and you give me the angle whose cosine is that, and it tells you 45.2. Okay? That's just good old trigonometry. Oh. All righty. So that's really, I mean, this is where the rubber meets the road as far as power factor. And the rate structure, well, okay, let's do this. This is called a lagging power factor in the industry. And it is said that the current lags the voltage because the current peaks first, the voltage peaks later. So this is a lagging power factor. The lagging or leading is in terms of the current position in terms of the voltage. Now, we'll see in just a second, I can correct this by adding capacitance to the system. And if I overcorrect, I can actually have a leading power factor, because the capacitance will retard the voltage wave. And so if I overcorrect, I can push the voltage wave further out in time from the current wave, and then I have a leading power factor. Well, guess what? They'll penalize you for both. I've seen bills where in the same month, they charged them a leading and a lagging power factor penalty. So what usually happens is the lagging occurs at maximum demand and the leading occurs at minimum demand. And so they're checking those utilities. I mean, they're out to scalp as much money as they can from you. So they're looking at all this stuff. Okay, on the lagging power factor, which is at the peak demand, they give you a certain amount of cushion before they start penalizing you. It depends on the rate. Like a GSA rate, it's 85%. They give you down to 85% before you start paying penalty. Below 85, they start putting a penalty on you. Larger rates, like this one you're working on, the threshold is 95. So the big boys are held to a higher standard than the little guys, okay? But on the leading side, if you go one step past one in the leading direction, they are likely to penalize you. Now, some do, some don't, because the leading power factor really helps the utility. But they can still penalize you for it, and a lot of them do. I've seen bills where they'll show a leading and there'll be no penalty, and I've seen bills that show a leading and they'll pay leading, lagging in the same month. It's up to the local utility to make a decision. But because most customers have lagging power factors, if you when you run a leading power factor, you're helping to correct for the whole system. So you're helping them out, but they may still stick you for it. Okay, so we said that. There's our 105.6 amps. Now, I said there's a little piece that is in addition to this, and the small piece is that at the higher amperage, you have higher line losses, I squared R. Just whatever the resistance of the wire is, current squared times that resistance is the drop for the current flowing through there. So if I push another 105.6 amps, I'm going to have a little bit of additional I squared R loss. A lot of times that it's not a huge number, but it is there. And a lot of times that gets left out of the analysis. So another huge advantage sometimes to the plant is that it's often the case that their electrical system, the MCCs, the motor control centers, power comes in with a big feeder, and then it's fed off to various electrical, they call them MCCs, like motor control centers, something like that. And so there'll be a lot of, they'll split it up. A plant might have 4, 5, 6, 7, 8 MCCs. And so if they're taking, maybe they're taking 5,000 kW, Maybe each one of these 5 takes about 1,000. Okay, so you got this MCC, and right outside the door, they want to add another electrical component, another motor, another gizmo, another fan, you know, whatever it is. They want to add to that. But that MCC is full. It's pulling its rated power, or, you know, there's not enough extra capacity in that panel to provide power to that motor. So if they're going to put that there, they have to expand the MCC. Well, that's an extremely expensive project. You have to redo the electrical service to that portion of the plant. But if you've got a number of loads coming out of that MCC that are serving devices that have low power factor, you can correct the power factor on each one of those loads, and then the current falls. So for example, if this motor was being served through that MCC, and I correct this from this 70, whatever it is, power factor up to 1 to 100%, I got another 105 amps of capacity in that MCC that I can use to drive something else. That can be as important, more important than getting out of penalty for a particular plant. So, you know, this thing cuts more than one different direction. So reasons to improve: power factor, avoid penalty, reduce current flows, reduce I²R, possibly unload circuits, transformers for additional electrical loads. And the voltage will be a little bit higher as you reduce the current flow, because the voltage drop is a function of how much current. So more current flow, more voltage you drop, you know, through the plant. So you may get a slight improvement in voltage as well. Okay, so let's talk a little bit about the physics. Y'all remember that building over there, Bruner? Anybody have any classes in Bruner? Down on this end of Bruner? Physics, good stuff. All right, so you remember this, right? The right-hand rule. You remember that? So I'm left-handed, so I just want to do it the wrong way, you know. But it's okay. So inductance in electrical circuits caused by the magnetic field around the conductor. Energy stored in the magnetic field produced by current flowing through a conductor, as described by the right-hand rule. So if you grab the wire, hopefully it's insulated, and the way your fingers wrap, that's the direction of the magnetic field. Not that we do care. So if that current's going up, you wrap your hand around it, that's the direction of the magnetic field. And that's energy. It takes energy to establish that field, okay? So the strength of the magnetic field is determined by the amount of current flow. The polarity or the direction of the magnetic field is determined by the direction. Now, so this AC power, and don't ask me to explain this because I don't know that I understand all of it, but you know, like it flows in different directions, right? It goes this way for a cycle and it goes this way for a cycle. Now, how in the world the electrons ever go anywhere, I'm not sure. You can go down the other end of the hall and ask them, and when you figure it out, let me know. But anyway, so that magnetic field, it's like as you go through that sine wave, as the current gets to its peak in one direction, that magnetic field peaks, and then it turns around and that magnetic field kind of collapses, and then it gets set up going the other direction because the current's going the other way. So that magnetic field is constantly flopping back and forth between this way and this way as that sine wave, you know, propagates through there. Okay, so amount of energy stored in a magnetic coil in air is very small and doesn't affect much of anything because air doesn't store much magnetic power. And it won't affect this phase relationship. However, if you make what, electromagnet, what do? You take a wire and wrap it around a bar, put current through the bar, and then you can pick up stuff, right? Well, why can't you do that if you wrap it around air? because there's not enough energy. There's not, that magnetic field is not strong enough. Wrapping it around that bar greatly increases the strength of that magnetic field. Okay. However, so when a wire wrapped around an iron core is in a motor, a transformer, an induction motor, the amount of energy stored in the magnetic field becomes very large. When this energy is returned to the circuit, it has an effect to cause the current waveform to lag the voltage waveform, i.e. causing a lagging power factor. And that's some pictures just of some, you know, coils and stuff from motors and whatever. Okay, so if you look at, you know, a portion of a waveform, so with an AC circuit, current polarity direction changes every half cycle. Therefore, the polarity of the magnetic field changes every half cycle. So, you know, it's pointing this way for a half cycle, and then it's pointing this way for a half cycle. And the amount of energy stored changes as that peaks and turns to zero and goes the other direction. So, with a sine wave of AC current, the current rises during the first 1/4 cycle from 0 to the peak positive value. So current comes up from here up to here, and as the current rises, the magnetic field gets stronger with more energy being stored in the magnetic field, okay? Well, maximum magnetic energy storage occurs when the current peaks at the end of the first 1/4 cycle. So up here, we've got maximum storage. During the second 1/4 cycle, the current starts trying to decrease from its peak. So it's trying to fall down to here because it's got to go negative to, you know, maintain the sine wave. Well, that magnetic field resists the decrease in current, and it returns that energy into the circuit, and it tries to maintain the current level at a higher level than it would be otherwise. So that energy is being sucked back in to the wire. So that returning energy basically slows the waveform down in time or causes a phase shift. And so anything that has a lot of inductance to it, it's gonna cause this phase shift. And of course, so we had those pictures before, so we've already seen that. Oh, I don't have to go through that again. Okay, at the half cycle point, that's where the current is 0. The polarity is reversing as the current, the direction of the current changes. And then we do the same thing in the other direction. So instead of the current going up, the current goes down, the magnetic field goes the opposite direction. And we load it up during that next 1/4 cycle, and then it collapses back into the wire. So this is constantly going on back and forth, and that causes that current waveform to lag that voltage waveform. Okay, and so we're just talking through all that stuff. Okay, so here you go. Capacitance is to voltage as inductance is to current. That's one of those SAT things where you got to do the analogy or something. I was never very good at that. In other words, the effect of capacitance in a circuit is to retard the voltage waveform relative to the current waveform. Thus, the addition of capacitors to a circuit with inductance can reduce the phase difference between those two waveforms and improve power factor. If capacitors are added to a purely resistive circuit, the current waveform will then lead the voltage waveform and give rise to a leading power factor. So this shows with a power factor of 1 or 100%, everything lines up like we saw before. But see here, the voltage is peaking after. So this is with additional capacitance in the circuit. The current will peak up here and the voltage will peak later. So it just changes that relationship between them. Okay, so how does a capacitor do this? So, you know, a capacitor is made up of two electrical plates separated by an insulating layer. And so the capacitor stores electrons on one plate as it gets charged. Okay, so as voltage rises during that first quarter cycle, electrons are stored on one of the plates. The peak storage occurs at the end of that quarter cycle, and then the voltage wants to start falling. Well, when that voltage starts falling, what happens to that capacitor? It starts discharging. It starts shoving those electrons back in the circuit. Well, the effect of that is to hold up the voltage waveform relative to the current. And so the capacitor then, the more capacitance you put in the circuit, the more you slow down the voltage in relation to the current. So by taking measurements and knowing what you have, you can adjust the amount of capacitance to match the amount of inductance, and you can set that power factor wherever you want it. As the voltage tries to fall, capacitor returns electrons to the circuit with holding the voltage higher than it would be without the capacitor. The second quarter cycle, capacitor discharges. And we do the same thing on the bottom side. Okay. That's by adding in the correct amount of capacitance to an electrical circuit. Power factor can be adjusted to any desired value. Practical rule of thumb is to raise the lagging power factor enough to avoid penalties. So the payback in this is to get out of penalty. If you're not being penalized, don't worry about it. It costs more, the little bit that you gain by just improving power factor, if you're not in penalty, is not worth the investment. But if you're paying significant penalty, it's a great investment. You're talking a 1 to 2 year payback in a lot of cases, which is pretty good return on your money. Here's an example. This is good. So this is maybe pretty close to the other. Yeah, this is about, relates back to that previous example. Okay, so we got real power of 100 kW. It doesn't change. Real power is real power. Okay, so the initial power triangle is this big one, and the apparent power is way down here, and that's your reactive power all the way up there. Well, so the reactive power on the initial power triangle is 100 kVAR. So, you know, so that's, I guess that makes, this is a right triangle, 45, 45, and 90 right there, because I got 100 and 100 and a hypotenuse, okay, from your trig. Okay, well, so let's see, let's get the calculator. So what's the power factor going to be in this smaller one? Remember, what's power factor? It's kW over kVA, right? Well, so before the kVA is 142 on this one, it's 105. So if I take 100 divided by 105, that tells me my power factor. So that's 95. Okay. So I'm gonna improve. I want to calculate the amount of capacitance I have to add to change this power triangle into this power triangle. Well, the way I do that is I reduce this side in order to make this triangle produce a ratio of this side to the hypotenuse of 0.95. Now, you know, if you're good at trig, there's lots of ways to calculate this. What I would do is I would say, okay, if I know this side and this side, I can calculate that side, right, by Pythagoras' theorem. So if I take 105 squared minus 100 squared equals this square root, I get 30, well, I got 32, shows 33, somebody rounded something, you know, whatever. So instead of being 100, I need this side to be 33. So guess what? 100 minus 33 is 67 kVAR. So I need to add 67 kVAR capacitors to this circuit, and this power triangle turns into this power triangle. I have then a power factor of 95%, and I'm out of penalty. Well, that's not so bad. You know, it's just stuff that is not commonly known. I don't know why. I guess because everybody in plants out there making widgets, and you know, the utility bill comes in and they give it to the accountant, and the accountant sure doesn't have a clue of this. He says, oh, okay, well, I know how to write a check. I'll write a check, and we go on to the next month, after month, after month, after month. And a lot of times nobody's looking at it. Okay, so look at that. Is that anything up there that you don't understand? Yes, sir.
So why would you not just add enough capacitance to make your power factor?
I'm sorry, what now?
Why would you not add enough capacitance to make your power factor 1 rather than just going to 95?
Oh, you could. It's just you would have to spend more on capacitors, and that incremental investment doesn't have a very good payback.
Okay.
See what I'm saying? The big savings are getting out of penalty. You know, you're only going to save, if you go on up, you're only going to save that I squared R. Because you will reduce the current a little bit more. Absolutely you will. Okay, and you can do, but once you get to 95, then no penalty. And let me show you. Here's a plant. Let me show you. See, there's one problem with this course. I run out of semester. I have one problem teaching this. I just run out of semester. Let's see. Excel. I think I already had this up there the other day, but you see not. We're not showing power factor on this thing. Shoot. Usually we put, well, okay. Let me see. The glasses are full. What doggone it? Is it full? Yeah. Well, okay, these guys had capacitors. Yeah, maybe I got it down here. Let's see, man, I'm fogging up here. Huh. I could have sworn. Anyway, these guys were running 95. When you looked at it, it was 95, 95.2. There might have been a 94.8 or something like that. But it was right there. And you look at it, and you just look at that and you go, you guys are correct, aren't you? And walk in and say, yeah, we got capacitors all over this place. And I mean, it's obvious they had already worked the problem. They'd already solved it. So anyway, I thought that was on here. Most of the time, if it's on the bill, we get it. This is our spreadsheet we do, but didn't make it, sorry. Wasted time there. What did I do? Shutting down my PowerPoint? Oh man, some days. I've got too much stuff open and I'm choking this computer, I think. I don't know that there's really a whole lot more. Yeah, right there. Thank you. Okay, this is, let's see, an estimate of the, let's see, typical electrical distribution system will suffer 2% overall as current flows through the resistance wire. So this is a rough and dirty way to estimate the change in line losses. So this, if you take 100 minus 100 times the ratio of the power factor before and after, then I don't know, I haven't run through these numbers in a long time, but anyway, you can use this equation to give you an estimate. So this one comes out, I guess it's 2% of 29%, and which is like 0.58% as additional savings from reduced line losses. So that's pretty much down in the weeds a little bit, but it's typically there. There are tables out here. If you don't want to do Pythagoras' theorem, you can use tables. You know, desired power factor, original power factor, and you take that fraction times the kW, I believe, and it'll tell you how much kVAR that you. Let's see if that works. Let's see, we were about 70% before, right? And let's say if we wanted to go to 95, so if I take 100, what's that? So 100 times, so that's about 69.1 kVAR. That's in the ballpark of what we were adding. I think we said add 67, something like that on our calculation. So kind of the lazy man's way of estimating this. Okay, now let me say this. Most plants, if you put meters on the whole service and you log that power factor like every minute or every 5 minutes or something, it's going to jump around, right? Because you got stuff coming on, going off, you got all kinds of interactions in the plant. So depending on how much variation, let's say you put in one big capacitor bank for the peak, but then that falls off and then you overcorrect like crazy and you get into problems on the other side. So what you could do is you can put in a switching bank. So let's say we have to put in 1,000 kVAR capacitors. We could put in 5 200 kVAR banks, and they have control systems that monitor the power factor, and they switch those in and out of the circuit in order to get you, a fairly stable power factor, so that you don't way overcorrect or other times way undercorrect. That's called a switching bank. And that's a good idea. It just ups the cost. If you can get by with one big static bank, well, it's cheaper. And so if your power factor doesn't move around, if it just sits there, then okay, you can do it with one bank. If it jumps around all the time, you're going to have to break that up into little modules, and you're going to have to put some switching in it. And the only way you're going to know is to put a meter on and record that for a while. These days, the utility meters are getting better and better. A lot of utility companies have this data. They save like a year's data on each customer, and they can just give it to you, like, I don't know, 15 or 30-minute interval data, and they can show you that. I can show you some interval data. I know I've got this, if it's open. Let's, not here, but this is form. I know I got this. So we got a year's worth of interval data for this forum. And so this is, Some of this is stuff I've calculated. I guess like this, A through I came in from the utility company. And so this is every 30 minutes they get a reading. So there's the time, there's the date. It starts July 1, 19. It's 29, there's the time. 12:29:59 a.m. is when the meter's recording. And so there's the plant KW, and there's the plant KVAR. So right there. And so I've got this every 30 minutes for the entire year. And so you can come down and so you can see the variation on this. So see with something like this, well here, I don't have a plot of this, but if we go this, insert. I haven't looked at this because I don't think we're doing anything with it. But. So there you go. There's how their KVAR, whoops, come on, little computer. My poor computer. I need to shut something down, I think. Oh, there we go. It should still be there. Whoops. What in the world? Well, where did that go? Gummit. For bad luck, I have no luck at all. There it is. Okay. So, and then you'd have to spread this out and look at it. But, it looks like they're spending this KVAR, spending most of its time between 2,000 and 3,000. That big dip is when the plant is down for maintenance for 2 weeks. You see something like that. So anyway, but that's what, if you're going to get in and do a serious study, you'd probably get an electrical engineer who, has much more expertise than we would in something like that. And let them dig into this. Okay, enough of that. And so that's not going anywhere. Let's just see. This ain't been difficult today. All right, I'll do this. All right. There's nothing there we hadn't already said. No, go into VSDs, solid state. You can read over this stuff. I think there's an example. That's a customer a number of years ago. So what do we got there? We got KWH cost, KW, apparent power, build demand. Okay, so now let's talk about how this gets billed, the penalty gets billed. This is a smaller rate structure. So this is a GSA, probably GSA 3 rate structure. So what happens here is notice you have actual KW and you have billed KW. The difference in those is your penalty. Okay, so what they do is they will give you down to on this rate, they'll give you down to an 85% power factor. And then if it's less than that, they calculate, They calculate a kW difference. We'll have to, I can't remember it off the top of my head. We'll look at a rate structure here in a second. But they have an algorithm, they calculate a build demand, and they compare these two. And if out of the algorithm, if it's a bigger number, they bill you for this demand instead of the meter demand. The actual demand is what came out of the meter. The build demand is what they got charged. The difference is their penalty because their power factor was low. Okay. And so you can see, let me see, demand charges. This is the dollar amount. This is the power factor over here. So you see all of these are below 85%. And so that generates a penalty in every month for them. So their penalty, they were paying about $3,500 a year. And from this information, you can go back and construct the power triangles and estimate how many kVAR capacitors. We usually use like 60 or 80 bucks a kVAR as an installation cost. If they have to do, if you think they have to do switching, you might do 100, something like that. And you can get a rough payback on something like that. This shows if you took the same bill and took it to a 95, I guess that's at an 85%. Just for fun, I ran this at 95%. And you see now at 95%, that penalty's up to almost $17,000, which starts to get, some people's attention a whole lot more. Even though that's not the rate structure they were on. I just did that as an exercise. This is fairly typical. Okay, so on the rate structure you have, they measure the kVAR. There is an allowable kVAR. Anything over that, you have to pay. You pay based on the kVAR instead of going through this kW thing. And so I think your rate structures, it's like $1.46 for a lagging kVAR, and it's usually something like between $1.10 and $1.20 for a leading kVAR. So anyway, okay, I think that's enough of this. Let's look at that GSA rate structure real quick, because we haven't done that in here. Power rates, GSA right there. Okay. So I don't know if we're going to see much of a difference here. And I was thinking that we would see, but these rates are all kind of migrating in the same direction. Service charge, admin charge. So we've got a GS, B, C, and D. Let's see. On peak, extra. This is the same stuff. So I guess they've all kind of, this is the same stuff we've already seen. There's no point in this. Okay. I thought this might look different. In the old days, the GSA rates were different, but this is not. Okay, well, I think that's going to be the end of my power factor and rate presentation. So let's talk a little bit about the steam stuff. And let's see. Okay, so this is the document that you'll have your quiz on. I think we won't have it next week. We'll probably have it a week from Tuesday, is what I'm thinking, to give you some time But I want you to read this first section of this thing. And it's really not bad reading at all. I mean, there's lots of, let's see. I know any of these people. Dr. Greg Harrell, he's a friend. He's now at Milligan University. Who else is? I know Jimmy Kamana. Who else? Michaela Martin. She's with Lockheed. She's not with Oak Ridge anymore. Sachin, I've worked with. Sachin was the one that sent me to Ukraine. I know Vestral. Tony Wright's retired. And Tom Winning, he took Tony Wright's position at Oak Ridge. So anyway, after a while, you get to know some of the players. Pretty good guy. So I want you to read, I guess, first 20 pages or so of this. Something like that. Rest of it, not really so interesting, but it's just general information about industrial steam systems. Yeah, quick start guide, where to find it. Steam system basics, why steam, operation, generation, recovery. Got a little cartoon kind of like of a steam system. Shell tube, boiler types. And some of this I'm going to lecture on in class, but anyway, it'll help your background on steam systems. So please be reading that. Okay. Yes, sir. A week from Tuesday. Not next week, a week from Tuesday. I've got to get it into iLearn. How are we doing? We got a few minutes. Okay, so, wow, this is just course divisions. Some of this stuff we'll do, some of it we're probably going to skip over. There's about 350 slides here, which is probably more than we have time to do this semester. So just to kind of set the stage here, and some of these numbers probably should be updated, but they still serve the purpose. Typically, industry consumes about 1/3 of U.S. energy. More than 40% U.S. natural gas consumed by industry. That may or may not, because now the utility sector is probably be determined or classified as commercial. I don't know if that would be commercial or that might be industrial, but we're generating a lot more electricity with natural gas than we ever used to before, because it's as cheaper than coal, and it's a whole lot cleaner. So anyway, by plant size, if you look at number of U.S. plants, and then those large plants, this shows about 6,800, or maybe fewer than that now. But of the percent, so those 600 or 6,800 use roughly 53% of the energy, of the industrial energy. So if you're going to save a boatload of energy, you need to go see the big boys that are using a whole bunch of energy. That's kind of the takeaway there. There's a lot of small ones, but they don't add up to such a big total. But that 6,800 big guys, some of those plants, that hurricane hit Port Arthur, hit around Port Arthur, Texas. The largest, Motiva has the largest oil refinery in the U.S., 600,000 barrels a day capacity in Port Arthur, Texas. I got to go down there for a week and look at their air compressors. And Errol Johnson is down there. He was the guy I worked with. He's a really good guy. I imagine Errol's up to here in water problems right now, because Man, they probably got 120, 130 mile an hour winds through a huge oil refinery. I can't imagine. I can't imagine the mess those poor guys have to work through and how long that plant will be down. Typical energy requirements, you can look, and you know, there is no one probably typical plant, but if you do the averages, you see steam accounts for roughly 35%, and process heating 38%. Well, steam and process heating are probably natural gas driven. So you can see these guys are gonna burn some natural gas to make all this stuff go. Now, I mean, process heating could be electric induction furnaces, stuff like that. But I would say the majority of it is natural gas driven, especially the big stuff. Well, so one of the reasons I want you to read all that stuff is you will read about a lot of this different types of equipment. So you'll generate some background in this area, this kind of informational stuff, and get a general idea what some of this does. We'll go through a lot of this in detail in class, but you know, there's always something that falls through the cracks. Okay, so steam system. So this is a little bit of a cartoon of an industrial steam system. So we're going to start out with probably a small, simple system, and we're going to go through and we're going to add components to it. So up here, we're showing 2 boilers. That's what's up at the top. And that depiction would be of a water tube boiler. When you read, you're going to find that we have really 2 types of boilers for industrial applications: fire tube and water tube. These are water tube boilers. This is showing drums, those little circles. That top circle that in blue is the main steam drum, and the bottom is what we call the mud drum. Because guess what? Sediment and stuff tends to settle to the bottom. So these are reservoirs of water, and they have tubes. Hot gases are generated inside the box by burning a fuel, probably natural gas, flows across those tubes, creates steam. Industrial stuff, probably the majority of the time is saturated steam, but it could be superheated. These boilers can produce superheated. Water tube boilers are what utilities will typically use to produce really high pressure steam for our power generation. And I know it's a little hard to see, but these little kind of circular tubes are meant to indicate the steam generating tubes. And when you come out of here, this guy that kind of goes down like that and back up, that's meant to indicate a superheater tube. So the way these are drawn, it would appear that we're getting superheated steam. Now, you know, the guy that made these was probably just cutting and pasting and putting stuff together. So, but that's what I see when I see that. We got a blower on the front. We got fuel coming in, so that's providing combustion air. We got a stack going up. Big boiler will have a fan on the backside sucking out. So the fan on the front end is called a forced draft fan, FD fan. You'll get this in your reading. It's blowing air into the boiler for combustion. And if it's big enough, we need a fan on the backside. It's called an ID fan, an induced draft fan. And it's basically sucking the products of combustion on out of the boiler and blowing them across any cleanup equipment. Could be sucking them or blowing them, depends on the configuration, and then eventually up the stack to get rid of them. Okay, so we've got feed water coming in the top, and we've got steam coming out. After we superheat it, it comes out. We're showing both boilers feeding into this pipe. That's called a header. That's like a supply pipe. Come out of the boiler into the header. The header runs out through the plant to distribute steam out to end users. So in this case, that would be the high pressure header. Actually, it's the only pressure header because there's only one, because this system is pretty simple. Okay? So we come out here into our header. And this is a heat exchanger, which indicates a process use. That's the purpose. The purpose of running those boilers is to provide heat to that heat exchanger so that it can heat whatever fluid is coming in cold and going out hot. That's a depiction of a shell and tube heat exchanger. Okay? So when that steam gets into that heat exchanger, the steam floods the shell, and then the liquid is inside pipes that may run back and forth inside that shell. The steam condenses on the outside of the pipes and transfers heat because that fluid's coming in cool and the fluid goes out hot, and the condensate falls down to the bottom of the heat exchanger, right? And it's liquid, but you want it. You don't want to throw it away because it's pure, it's been treated, and it's hot. You know, if you're condensing the steam, if that's saturated steam going in, the condensate is coming out at the same temperature that the steam went in, right? You're just going across the vapor dome from saturated liquid, or from saturated vapor to saturated liquid, a lot of temperature. I mean, if that's 100 psi, 100 psi A is 327 Fahrenheit. Well, that's pretty hot compared to 60 degree or 70 degree makeup water, you know, and you've already cleaned it up. So you want that condensate's valuable, so you want it back. So what's this little gizmo? How am I doing? I'll be doing this at 4:30 if y'all don't stop me. So what's this little box here and this little kind of lever or something in there? Anybody have an idea what that's about? Louder. That's a steam trap. Is that what you said? Well, yeah. We call that a steam trap, but that's what it is. It's an automated valve. So that's a float. That's what they're showing this one. And in your reading, you're going to read about 5 or 6 different types of steam traps that are out there. So what that little box is, with that little float job in there, that condensate comes in and builds up in there. When it gets to a certain level, that little float opens and the condensate goes out. It's kind of like a toilet mechanism, you know. It's automatic, because you don't want to blow live steam through your heat exchanger. If that was an open pipe, we'd just be blowing steam. We'd be wasting a bunch of steam. You'd have steam blowing into your condensate return system, which is a waste. You know, I mean, that steam's precious stuff. You don't want to throw it away. So the steam comes into the heat exchanger, condenses to liquid. It falls down here to this trap. When it gets full, that trap opens. Condensate drains down through that pipe. When that trap gets empty of condensate, it closes. So it protects live steam from being wasted. So that's the steam trap. And then you see it goes down to this little blue kind of guy down here. That's a condensate receiver tank. It flows back, and you may have to pump it. We may have to put something in and pump it to get it back to the boiler house. Depends on how big the system is. Sometimes they can flow, because you've got pressure up here. You've got whatever your boiler pressure is coming in here. So you've got pressure here. Now, when that trap opens, you've got pressure behind it. When that trap closes, not so much, you know, because there's nothing pushing. You got that closed off. And so the question is, can you get this back into this tank without pumping it? You may or may not. It depends on the system. Most likely, you're going to have to pump it. Like at Tech, in the Tech mechanical rooms, they've got these little package condensate receiver stations that have pumps on them. And so, you know, we're pumping steam into the building. We make hot water in the building. The steam condenses, falls into that little jobber down there. It's got a pump on it. and it pumps it back into the condensate return line, which pushes it back to the boiler house. Because tech wants that condensate back too. Okay. We've got another line coming down right here, and this is my high pressure steam. It's going down to this job. Oh, what's this guy here? Any idea? Got that funny looking kind of bump on the top of it. That's the deaerator. The purpose of that is to strip any oxygen or non-condensable gases out of the feed water before it goes back to the boiler. Because high temperature oxygen in that feed water will corrode holes in your boiler. You cannot allow oxygen of any concentration to be in that feed water, or you'll get pitting on your boiler, and after 6 months, a year, 2 years, depending on how bad it is, you'll have leaks and holes, and you'll wind up replacing major sections, piping, tubes, whatever, in your boiler. So this is the deaerator right here. This it's really up here, and then this is a tank that once the gases have been stripped off, it gets stored here, and then it gets pumped back to the boiler. Okay, so you see this condensate comes back, and it comes over here and goes through the deaerator, and this is your makeup water, because guys, whatever steam you put out here, you don't get it all back. You may want it all back, but you won't get it all back. There's leaks, there's this, there's that. Sometimes some of that steam gets direct injected into products. It gets contaminated and it doesn't get cleaned up. And so you just dump condensate. Sometimes it's too far. A big plant, it might be 1.5 miles down there where that steam gets used. It's just too far. We're not gonna bring it back. They just dump it out on the ground, pour it in the sewer, whatever. So you're not gonna get it all back. And so you're gonna have to put makeup water in the system. And this is the makeup water flow. These two little kind of rectangular jobs represent water treatment. Now there's lots of different types of water treatment. That's kind of what tech looks like. The tech has water softeners, because we don't run a lot of pressure. Higher the pressure, the better the water has to be in order to not cause problems, corrosion, scaling. If you put minerals in, they will eventually, if the concentration of the minerals gets too high, they will scale out on your heat transfer surfaces. So lots of bad things happen if you don't do your makeup, properly clean up your makeup water. Yes, sir?
So reusing the condensate from the heat transfer, how do they?
Makeup water. It'll be like in this case, sure. Someplace you'll have a level switch that lets you know when your system is getting low on water. And so if the water goes below a certain level, then you crack a valve and you run water in over here. This is not a very sophisticated system. You know, what might happen really, this water might go in this tank. That's probably what would happen. And then you would have a level over here, and say you have to continue to feed the boiler. But if I'm not getting enough back here and I continue to feed the boiler, then the level in this tank will start going down. And in which case that would open a valve, and this would probably really get put in over here, and then this flow up together. But that's just not the way that diagram happened. Absolutely. Okay, that's pretty good. So that's that. So we're going to stop here in just a second. Now, all of a sudden, hold on. What do you mean? Oh, is it time? Hold on. I got 1 minute. Okay, so the next level of complexity, we put in another header. Now, see, we have high pressure steam. We have low pressure steam. Oh my gosh, we got turbines. We got a pressure reducing valve. Oh my gosh. And so we have this and 2 more levels of complexity before we get through this general discussion of the layout of this steam system. Okay, now I'll let you go. So y'all have a great weekend, stay safe, and see you on Tuesday.